Welcome everyone to today's webinar. We're going to wait just a few more minutes for everyone to join us, and then we'll get started. So while we wait, please note that this event is being recorded. The link will be available via email after the webinar has concluded. You won't be seen or heard, but if you're still not comfortable with the recording, we invite you to sign off now. In today's session, we're going to cover the use of Spark for proving software security. Today's topic builds upon our last two Spark webinars. We will illustrate how to use Spark Pro to prove that code complies with its specification, including the language to express this specification and the process to successfully prove that compliance. I'm Tony Aiello, one of the product managers at Adacore, and I'm responsible for Spark. If you have any questions during the presentation, please use the tab at the bottom right of your interface and ask your question there. We'll answer these questions during the Q&A session at the end. Before we dive in, I'd like to say just a few words about Adacore. Adacore is a tool provider for high-integrity software. We were founded in 1994, and we have about 150 employees worldwide. Our technology is used in a wide variety of products across the world. We bring expertise in embedded and high-integrity platforms. At Adacore, we develop tool chains for a growing number of programming languages, Ada and Spark, C and C++, and Rust. Our goal is to be your one-stop shop for high-integrity and safety-certified embedded needs. Without further ado, I'll hand off to Yannick Moy, Adacore's head of static analysis and one of the lead developers of Spark.
Hi, everyone. So this session is the third in a three-part series that we gave on Spark that is available on the Adacore channel on YouTube. In the first one, I showed that Spark is a good fit for embedded and systems programming. In the second one, I focused on proving memory safety with Spark. And in this session, we're going to prove software security with Spark. So let's go back to the basics of software security with the CIA triad, which stands for confidentiality, integrity, and availability. To ensure these properties, we need to guarantee that the attacker cannot execute arbitrary payload, otherwise all of CIA are compromised, that the attacker cannot crash the program, otherwise availability is out of the window. But even if we don't go to these extremes, we don't want the attacker to also starve the program from the needed resources, which can result in a crash or in a degraded mode where the program cannot fulfill its intended function. And so more generally, talking about that, we don't want the attacker to subvert the intended function, for example, by bypassing security checks. To prevent the first 2.5 problems just mentioned to happen, we've seen in the previous webinar that we can use Spark to prove memory safety and absence of runtimers, thus achieving what we call the silver assurance level in Spark. And today, we're going to show how we can address the final problems that we just mentioned, thus achieving what we call the gold level of assurance in Spark. So how can we express and verify the intended functionality? Well, we start with a natural language expression of a functionality in general, and we're taking here the example of the Ada reference manual, just one function, the open function in unit ada.txt.io, which is described in a sequence of paragraphs. And I've highlighted here in bold sentences that I will read aloud. Open sets the current mode of the given file to the given modes. The given file is left open. An exception is propagated if the given file is already open. And after file with mode out file or append file is open, the page length and line length have the conventional value 0. From these, we extracted this contract on ada.textio.open in our version of the ADA standard that ships with GNAT and Spark, so that you can analyze safely calls to open in a Spark program. And you can see here in the precondition something that prevents from passing in a context where an exception would be raised at runtime, corresponding to the fact that the exception is propagated if the given file is already open. In the first line of the postcondition, we can recognize the specification, the given file is left open. In the second line, another part of the specification, and in the third, fourth, and fifth line of the postcondition, yet another part that I highlighted before in bold. So here we could do that because the API of ada.textio already offers this is-open functionality. Then you might wonder how to do that in a systematic way, in particular if the API doesn't offer such facilities. And this is where automata come to the rescue. Indeed, resources are usually accessed through an API to acquire, use, and then release the resource. For example, files are first opened, then used, finally closed. Sockets are connected, then used, finally disconnected. And memory is allocated, then used, finally freed. Similarly, the state of the system and objects of the system dictates what actions are allowed on the system and objects. For example, an access is granted only after a password check succeeds, or after an error is signaled, only recovery actions are possible. And automata allow to express such allowed transitions between states. So let's take a very simple example of an automaton for a memory allocator. So we'll assume that a function alloc gives us an allocated chunk of memory from which we can write to the chunk to get it in an initialized state, and then repeatedly read and write the chunk of memory. In each of these states, we can move to the freed state by calling the free transition. This automaton can be readily expressed in Spark with what we call a ghost type here status. So ghost means only for verification. And this type status has these three states that we just mentioned, allocated, initialized, and freed. And we define a function state, also a ghost function, which is going to tell us what is the state of the parameter chunk. Note that this function state is marked as import, which means that it doesn't have any implementation. It doesn't have support in the actual program to be executed. It's only here for verification with Spark. And armed with this type and function, we can now annotate with contracts all of the function of the API, alloc, free, write, and read, to have suitable precondition and postcondition to express when they can be called and what results from the call. For example, alloc returns us a chunk in the allocated state. Free returns with the parameter state in the freed state. Parameter chunks, sorry, in the free state. Write will take a chunk either in allocated or initialized states and will return it in the initialized state. And finally, read will take a state only in the initialized state. And you can see that write has an additional postcondition to express that reading after write will return the value written. Now, we might wonder what happens if we violate the automaton. And classically, we can extend the automaton with an error state with all these transitions that are not allowed. So for example, read in an allocated state. And this will result, during analysis with Spark, in a precondition error. So for example, here, when we start with an allocated chunk of memory, we can prove that it's in the state allocated, but we cannot read it because the precondition prevents it, and we get in the error state in the automator. After that, we can write to the chunk of memory, and we can prove that this is in the state initialized and that reading it returns the value written. We can write again. We can free even, but after the state freed has been reached, we cannot write again. So let's see that in the editor. So I could have chosen Visual Studio Code or GNAT Studio. Here, this is GNAT Studio. And you can see this simple memory unit here with the Go state status, the state function, and the contract that I just shown. Now we can use this unit and call Spark analysis, which highlights these two lines that I presented with the precondition failure here. So let's remove this call because we know they are erroneous, and reanalyze the color here, and everything is proved. Now this also extends to implicit transitions between states. When we manipulate a memory allocator, we'd like the states to the memory to be released before it's finalized, so before the variable is reassigned or its scope ends. That's what we call finalization in Spark. And so we can complete the automaton here with a finalization transition that comes to the error state. And again, this can be expressed in Spark. So here we can say that the type chunk has ownership with a given annotation here, and that it needs reclamation before variables of such a type come to the end of life. We have various ways to specify that something has been reclaimed to a constant or a function. And so here we chose to do it with a function isNull that has this annotation to state that if isNull returns true, then the corresponding value has been reclaimed according to the ownership principle associated to this type. And to relate that to the state function, we add a postcondition to isNull to state that isNull is true exactly when the state is freed. Now, when we look at the usage of this memory allocator, if we do allocate the chunk and then write it, which is correct, but forget to free the state, now we will get an error saying that memory chunk C has not been freed. So we can, again, look at that here in the editor. So that's this simple own memory. And here we have this chunk which has the annotation for reclamation with the function isNull. The contracts have not been modified, are the same as before. And we can now look at the usage of this memory allocator with ownership and analyze it. Here, free is not called, and we get, as expected, a message, a check message saying that the resource or memory leak might occur at the end of the scope. And of course, if we now include the call to free, this is proved correct by Spark. So in the two cases that we saw, two solutions, there were some limitations. So in fact, we only verified the API usage. Indeed, the postconditions were calling imported ghost function, so a function that has no basis in implementation, so we cannot prove after the execution of the body of the API that indeed the state is as we specified. In addition, the ownership annotation that we put in the second solution is only valid for a type that is a black box for Spark, so its full view should not be in Spark. Another limitation is that the state could be more complex than the enumeration or type state that we just used. The state could depend on the call parameters when calling the functions or procedures of the API, or the state might have a numerical part. So we'll have two goals now, both to verify the API usage implementation, and second goal, to be able to express more complex properties. And for both goals, the solution is still to use queried ghost functions, but not imported ones, instead implemented ones. So let's take as a challenge to extend this memory allocator with the right function that writes to parts of a memory chunk, not the full memory chunk. We'll have two solutions. In the first solution, we will extend the Ghost query API. So we'll have a way to keep track of the prefix of the memory chunk that has been initialized. So we have the function isNull, Ghost function as before. We have now a function size that gives us the size of the chunk. And the function isInitialized, also Ghost, that tells us from a given position to a given position, that the chunk has been initialized. So that's when we call write, we're able to show that this chunk of initialized memory has been extended. In the second solution, we'll go for a ghost model of the data. What this means is that we have a function here, model, that is a ghost function, that returns a value that represents the data. So we could have more than one. Here we have one. So it's the most precise and flexible solution. Here we'll have this model string for the content of the memory chunk. So type str is this type that models what there is in the memory chunk. And we'll have the same ghost functions for isNull and size. So let's look at it in the editor. So we have memory here. So as I said, we have isNull, size, and isInitialized as ghost functions. We have just a function big to rename a function from the library to big integer. So to be able to express arithmetic properties without worrying about possible overflows. And we have alloc and free mostly as before with this call to size function here in the post condition of alloc. And the interesting bit is in the write function here, where we can use this big function to express arithmetic in arbitrary integers. So we don't need to work our way to use only machine integers here. Quite convenient using an unit from the Spark library. And this post condition that states that after the call to write, well, we've initialized up to data length more than what it was initialized before. So we are extending the prefix that is initialized. Plus the usual post conditions about read here that states that what was initialized before still has the same value, and what has just been written between from and this index is exactly the data we provided. And basically that's it. Now the implementation is also in Spark. You cannot see any mention of Spark mode off like before, and the implementation as well. And we can verify this implementation in Spark, first thing. And also use that implementation and verify it again. So here, as you can see, we write first hello, then world. So this first session shows that, like before, we cannot call read before the memory has been initialized. So let's remove that error. Reanalyze. It results again in an error because after the memory has been freed, we cannot write. So let's remove that error again. And now we have a correct code, which allows us to write in chunks the memory. So first 6 characters here that we can read, and then 7 more characters, and we can read the whole chunk afterwards from 1 to 11, and it's what we expected. Let's just look now at the version with the model. So here we have this isNull and size ghost functions like before with this new model. And the model is implemented here in the private part, returning the whole content of the chunk, which is a pointer here. And again, as before, what's interesting is the write and read parts of the API. So now write has still the same precondition to avoid overflows when extended when computing indices from this position using the length of data. And we have this post condition which states that this new model in the range starting at from is exactly the data that we provided, while before this range and after this range is just the model that we had before. So that's model of the chunk tick old. That's a way to denote the value of this model before the call with the suitable indices that haven't changed. We have the same for the function read here. So saying that reads returns the actual model of the string in the range denoted by the parameters from and to. In fact, we don't even need this postcondition here because reads is defined in the private part, so that would be available for proof. Again, we have an implementation that is in Spark, We can analyze this implementation against its specification. It's proven, and we can use it. And so now I did plant erroneous assertions in the program, so it's all proven. And you can see here that we can write in any order, so we can write the second word before the first one. That's fine. So to allow us to do all this specification, we have a rich language for specification in Spark. There are contracts on packages, on subprograms, on types, on variables. Inside these contracts, we have sometimes rich expressions, and there are many kinds of expressions. Some of them we haven't seen during the 3 webinars. Expression functions to factorize queries. So we saw many of them. If expression and case expressions, so the equivalent in expression of the statements to express distinction between cases. Quantified expression that allow on a collection to express conditions for all elements or for only some elements. Declare expression that allow us to introduce local names, but without the need to extract this expression in an expression function. And finally, delta aggregate, so a special kind of aggregate to express how a composite value, like a record on an array, is partially changed. We also have special attributes for specification. So we saw some of them to relate the pre-state and post-states in a call or around a loop, or the result of a function, or what part of an object is initialized. And we have many more aspects and annotations that allow us to deal with specific of a program for verification and specification. In addition to that, we have a full verification language that supports helping the automated tool come to a proof. In addition to all of the assertions that we saw, we also have ghost code. So we have this ghost aspect that we can attach to a number of entities. For example, ghost functions, which provides a way to express additional queries that are not available in the API, but that are useful for specification and verification. That includes imported ghost functions, when we have such functions that cannot be executed, but are still useful for specification and verification, like we saw. We can also have ghost variables, types, procedures that support the verification code. And an important case of such ghost procedures is what we call ghost lemmas. These are procedures which have no effect, but they expose a contract between its precondition and postcondition that states an important property that we can prove separately and use. And we'll see an example. And that really helps with what we call the auto-active approach, where we help the automatic provers with a limited amount of interaction. A ghost code is this code marked ghost. It is executed when we check assertions. So that can come because we specify the switch NAT A during compilation, or because we use pragma assertion policy with the right values. But it will be ignored when compiling for production code without assertions. And note that ghost code is always used for formal verification. The crucial property here is that these ghost codes shouldn't interfere with the normal codes, and this is verified by Spark. So now let's look at 2 cases of autoactive features that are helpful in this approach. The first one is loop invariant. So I'm taking here an example from the GNAT runtime library. So here is the function times or star on characters from the library ada.strings.fixed. Essentially, if you call 3 times a character, you want the string that consists in 3 times this character. The implementation is what you would expect. So we return here a result variable, and inside this loop, we initialize every character of the results with the right character that has been passed as parameter. What we need here is a loop invariant to state that after the nth iteration of the loop, or the jth iteration here, all of the characters that have been initialized so far indeed result in the array result being initialized at this position, and the array result having the right character at this position. So the loop invariant summarizes the first n iterations of the loop, so that automatic provers can prove it and use it to prove the postcondition of the function, which is not shown here, but which is the actual functional postcondition. Let's now look at ghost lemmas. Here we have another overload of the function times. This time it's for having the same string repeated n time or left time with the parameter left here. And we need, in fact, sublemmas because this will involve use of the mod operator, which is sometimes difficult for automatic provers. So there needs to be some help here. And the help comes in the form of these lemmas. So a lemma is a ghost procedure with a precondition and postcondition. And it essentially states that when we know the precondition, we can deduce the postcondition. This allows here to extract difficult parts of the proof to a separate procedure. So it's proof in isolation. It turns out that this lemma mode has a null body. So just extracting this property makes it provable automatically. But this lemma mode is called itself in a more complex lemma, which needs a body to be proven. And this more complex lemma is used in the actual body of the function types. And this allows to prove the functional specification of this function in our GNAT runtime library. So now, who is using Spark in this way to prove software security? So a few names here. SecuNet, company SecuNet, has been using Spark for 15 years to prove security at a high level involving government certification for things like gateways and parts of workstations. The Swiss company Code Labs has been using Spark to develop the open source Muen separation kernel in Spark, proving various properties on the code, and more for more than 10 years. And more recently, NVIDIA, well-known global company, has been using Spark, so for the past 5 years, to prove the security of many different parts, like the boot ROM, their hypervisors, security function from automotive software, verification of the GPU, overall GPU firmware image. So I'd love to add your company logo to these slides next time. And so for this, if you want to know more, you can always return to this 3-part webinar, which will be available on YouTube once this session is done. And there's also the learn.educore.com if you want to look in more detail at some of the ways that Spark operates this verification. Otherwise, please contact us and we'll be delighted to continue the conversation.
Thank you, Yannick. So this brings us to the question and answer part of our session. So far, nobody's asked any questions. So please ask questions. We'd be delighted to engage with you by answering them. While I wait for questions to hopefully start pouring in, I will let you know that everyone who signed up for today's session will receive a recording of the events and an email that will be sent out after we're done. So you can keep your eyes open for that. You'll also be able to download the slides. You can do that right now by clicking on the apps button in the lower right-hand corner and selecting handouts. And then, as Yannick mentioned at the beginning, our previous webinars in this series are now available to watch on YouTube, and you have the links for those as well.
And while we're waiting for questions, I would like to insist that a lot of the material that I presented may be completely new to you. So don't hesitate if some of the things I presented were unclear. That's also something we'd like to address during this Q&A session.
We'll hang out and wait for just a couple more minutes and see if anyone wants to raise a question. I feel like I should have some kind of clever anecdote to share, but I don't.
And I'd like to add that this concept of ghost code is very powerful. So I've presented very simple ways to use it here, but it's really coding the verification. And so it really appeals to programmers because once you've expressed your properties, well, you'd like it to go through the most easily possible, but that's not how it works for complex properties. And here, Ghost Code provides you a way as a programmer to really make progress towards full automation without resorting to some magic means.
Okay, so we have a question. How would you do taint analysis to avoid leaking secrets?
So here I presented functional verification. So when you go from some properties in input to some properties in output, so it's not directly applicable to taint analysis where you want to check flow. And one part of Spark actually does flow analysis. In fact, Spark has two components, something I presented last time. And the first part, which is called flow, precisely analyzes how all inputs flow to outputs. So one way would be to add contracts in the form of this global contract that states what are the inputs and outputs, and depends contract, which states how inputs flow to outputs, and have Spark verify those dependencies. So you can precisely define how you expect this or that part of the software to derive its output from its input. So that's one way. Another way would be to encode your taint analysis in an automaton, like I showed for the memory allocator. So indeed, if you can state that an object is initially tainted and that you need to have it go through a sanitization function before it gets the states untainted, and you can use it further, then you can use exactly the verification that I showed. So that depends on having this interface, this API that you can expose for the objects that you want to see as tainted or untainted with the corresponding sanitization functions.
I'll wait maybe 2 more minutes and see if any other questions come in.
Yeah, and in case you're curious, you can go much further. The examples that I showed, you can prove complex data structures with this kind of methodology. That involves not having only contracts on the API, but usually having a type invariance of some sort. So there are various kinds of type invariants that you can use in Spark, in addition to the contracts on the API. And maybe a last bit is that the initial examples that I showed, where the verification is only on the usage of the API, is something that is very convenient when you define a wrapper on a library in another language, whether it's plain Ada or C or another language, because then you can expose in the API exactly the kind of usage that you want, even if, obviously, since the library is done in another language, you're not going to formally verify that these contracts are implemented in the code, but you can expose the usage that you want.
We have another question asking if we have any plans to extend this to Rust. I also, one of my other hats is product manager for Ganat Pro for Rust, Data Core's offering in the Rust space. So I can say that as of today, we do not have plans to extend this kind of reasoning capability to Rust. There's a variety of reasons for that, which really hinge around product. But the simplest and most technical answer to that is today, the Rust language lacks features that are needed to enable the kind of precision that allows these sorts of proofs to succeed. So one of the features that was covered in prior presentations, prior webinars by Yannick, was the ability to use subtyping to put narrow ranges on things like numeric types. And Rust doesn't have that kind of facility. And you need that in general to be able to reason precisely about arithmetic statements to ensure that you're not going to have overflows or errors. And that then feeds into your ability to state a proof of correctness, let's say close to total correctness, for the code that you've written. So from a technical standpoint, that's why I would say no today. Also for various product reasons, it's not something that we're currently focusing on. There are efforts in the academic community and in the research community at large to look at Spark-like approaches, I would say, functional verification approaches that rely on similar kinds of technologies under the hood. So I would invite you to look at those if you're interested. Yannick, did you want to add anything?
Yeah, I can just add that, as you said, Rust verification wouldn't actually work exactly like Spark. The tools that are available today, for example, don't rely on the possibility to execute contracts because Rust has means to express ownership that are different from Spark and that make execution of contracts much more challenging. On the other side, there are interesting academic projects that we are aware of. We are actually even participating in the research projects today with people from INRIA developing Creusot. So that's an interesting perspective for the future.
We got a follow-on question to this, querying whether the volatility of the Rust language, that is its rate of change, was one of the features or one of the reasons that we're kind of staying away from it. I would say that could be viewed as a factor, but for me, it's not the most significant factor that causes us to not want to dip our toe into that pond just yet. If you do have any other questions, if you think of things later, then please don't hesitate to reach out by email and ask those questions of us. And oh, wait, another question just came in. Well, I'll finish my statement. We'd be delighted to engage with you and to answer your questions, however you get them to us. Are more features of Spark going to be proposed to be included in official ADA? That's an interesting question. Yannick, do you want to take a stab at that and then I'll follow up?
Yes, so it has happened in the past. So for example, delta aggregates in the latest version of ADA 2022, was a direct consequence of Spark starting with a specific attribute, which was called update at the time. And we made it obsolete as soon as the new version of ADA came up, and we could translate the use of this ad hoc attribute into a new expression form in ADA. On the other side, so this was because it's a capability that is useful for specification in general, beyond the use of Spark as a formal verification technology. There are other things that are mostly useful for Spark. So today, for example, the ability to state global variable written and read by subprograms remains mostly implemented in Spark. It has been through a formalization for ADA in ADA 2022, but for example, this part of the specification was not implemented in any compiler so far. So there needs to be care in how some features remain with Spark, and especially because ADA language is perfectly fit for having specific aspects, attributes, pragmas that only apply to a given technology like Spark, and moving some of these that are generally useful and interesting for other tools to the main language.
We have another question. Are there any plans for temporal aspects of verification like TLA plus that might be added to Spark?
So not today. TLA plus relies on a specific language with a much smaller code in general to be applicable. With Spark, we're looking at much larger code bases. So there's a scalability issue here. And today we would recommend using TLA plus on a model of the software and then moving to implementation with Spark focusing on correctness of the implementation, consistency of the implementation, correct implementation with respect to specifications, verification of properties that can be expressed with contracts, these kind of things.
Yes, well, I'll note that this is a rich topic. So if you do want to discuss with us further how to do temporal modeling in Spark, that certainly is something that we could discuss. Temporal logic, linear temporal logic is formalized in terms of first order predicate logic. So it's theoretically possible to encode relevant temporal logic properties using the capabilities that Spark offers. The provability after you have done that becomes challenging depending on how complex the situation actually is. So, again, if this is a topic that's particularly of interest to you, if you want to understand what could be done with Spark or, think a little bit about how to apply this to your domain, please don't hesitate to reach out.
And I would like to add that if your temporal properties can be expressed as an automaton, then you can use the techniques that I presented before.
Right, indeed. Are there performance benchmarks and comparisons between Ada Spark to other native languages such as C, C++, or Rust that are available?
I mean, Ada is a compiled language. In particular, when you're using Spark, you can compile without any of the checks once you've proven that none of them can fail. So you can be as efficient as C or Rust. Now it really depends on the application. So there are some papers that have comparisons in terms of size of the binary, running time, memory, energy consumption. So you can find out some of these, but really what you should do is look at your application and how you can express it in C, Rust, C++, or Ada. Ada Spark, because really for compilation, that's the Ada or Spark makes no difference. And you should get the same. Yeah, essentially, people who do that have no issue.
In the first presentation that we did, so the first webinar, there was a discussion of how features of Ada can really help you get low level, reasonably close to your hardware. And I would encourage you, if you've not actually seen that webinar, to go take a look at it. I think it answers some of the aspects of your question and dovetails nicely with what Yannick just said. There's a lot of capability in Ada that lets you get close to hardware and be very specific about what you want to do. We have a question. Do we have experience with the size of ghost code relative to real code for functional verification of real applications?
So yes, it can go very large if your application is complex. So for example, for the verification of red-black trees encoded of red-black trees for the embedded domain, so without any dynamic allocation, which means that all the cells of your trees are encoded as arrays in cells in an array, which needs a lot of work to manage the tree structure and prove that the tree structure is preserved when you balance the trees. Here, the ghost code was 10 times the size of the actual code. But of course, that depends on your constraints. So here, the embedded part, no dynamic allocation, was explaining a lot of the growth of this ghost code. When we did the same with dynamic allocation, the ghost code was divided, so it was only 5 times the size of the actual code. Again, because we were proving the full functional property of red-black trees, which is complex. Now, if you just look at simpler properties, so on these red-black trees, if you just prove absence of runtimers, Ghost code is insignificant. That's mostly the specification itself, and the Ghost code which helps with the verification is very small. If you go to just some of the properties, so instead of going for the full functional correctness, then size of the Ghost code is much lower, than this 10 times unfolding. We have another experience in a different domain with a lot of Ghost code, which is another part of our runtime library. So I mentioned these string functions in the standard library. We have other parts that deal with supporting the runtime of the compiler. In particular, unit that does multiplace operators, multiplace multiplication division using a subtle algorithm. One which is called algorithm D by Knut, and this one has again this multiplication of the size of the code by 10 to have all of the specification Ghost code lemmas that you need to prove this quite subtle code. The benefit is at the end. Why did we do that with these various bits? Because they were so complex that doing verification by review, by testing was not sufficient. So in the end, that was time and code well spent. And again, Ghost code is only code. So if for a very complex piece of code that is of a reasonable size, you incur up to 10 times, which I mentioned because these are extreme examples, we felt that it was time well spent. And for example, we use the fact that we prove part of our runtime library in our certification of the runtime library in that.
Thank you again, Yannick, and thank you everyone for attending. Again, as a reminder, you'll have an email that provides a link to the recording for this webinar. If you have any other questions, please don't hesitate to reach out to us. We would be delighted to answer your questions. Thank you all very much.
Do you want Tony to ask to reply to the last question?
In Adacor's opinion, will using formal verification tools like Spark on non-trivial programs start to become accessible to non-experts in formal methods? Yannick?
Yeah, so what do you mean with non-trivial programs, I think? Non-trivial is any program that is useful, and we have a lot of people using Spark on non-trivial programs in that sense. Non-trivial programs can have different levels of specifications, from simple specification to prove useful properties, what we call the goal level, up to full functional specification, which can be, again, more or less complex. So already it's available. You can use the open source tools to get an idea. You can use it even in this e-learning website, learn.adacore.com, and you'll see that it's quite approachable. So we believe that today we have the proof that programmers without a formal verification background can use Spark efficiently.
Okay, let's end here. Thank you all, and we hope to hear from you.
Thank you. Bye.